want to wish you a happy Valentine's Day. I did leave some Valentines at your tables there. I did not make them. I don't want to claim credit for them, but I do love them. And so I try to remember on the 13th to get my act together and, get them out so that I can share them with you. I wanted to share them all with you so you can see them because, we don't get to talk about, physicist history very often. And I'm not going to show every single one, but just a couple of them because they're kind of fun. So, this guy here, yeah? Mr. Isaac Newton, yeah. So the stuff fall, that's kind of funny. This is my very favorite physicist ever. Her name is Lise Meitner, and she is the physicist that discovered nuclear fission. So she is actually the person that figured out how if you've got a really, really large nucleus and you throw neutrons at it, you can get it to split into things. Part of the reason that I always want to kind of talk about her is that she did not actually earn a Nobel Prize for her work. The chemist that she was working with earned the Nobel Prize and did not mention her during the acceptance speech. It was a really big scandal, and she is super awesome. This was all during the World War II Nazi regime. She was from Austria, but was working in Germany. She's Jewish. So, there's a lot of other historical pieces to it, but she's also just exceedingly awesome. So there's that. Some of I'm just going to kind of skip to some of the other ones. You guys may have heard of Carl Sagan. Yeah, he wrote a bunch of sci-fi stuff. So anyway, there's a Carl Sagan shout out right there. Other ones that you may have been familiar with. You've heard probably of William Thomson, who's Lord Kelvin, right? Of absolute zero Kelvin fame, right? He's that whole temperature scale guy. So there's another one there. Absolutely zero reservations about wanting you to be my Valentine. Has anybody ever heard of Grace Hopper? Anybody know who Grace Hopper is? Yeah? Yeah. So she is the very first person to ever really develop and write computer code. So programming she is the mother of computing. And the reason that, or one of the other reasons that she is very well known is that she coined the term to debug, or that there's a bug in the code or you've heard that term, right? There's a bug, there's a problem, because literally they were trying to make this program work and there was literally a moth that was dead inside the large computer that caused the problem. So yeah, she coined that phrase, which I think is kind of funny, but we have a book about her at home. She was she worked in the Navy and she did a lot of programming for them. And they forced her to retire when she was 87 or something like that. She's like, I don't want to retire. And they're like, you need to retire. And then the next year they called her back and they're like, you need to come back because nobody can do what you're doing. So then she worked for another 5 or 6 years after that. She's rock star physicist. You know who this guy is? Yeah. That's Einstein. Yeah. That's Albert Einstein. A little before the crazy hair. Yeah. Yeah. That's Albert Einstein. Yep. Yeah. When he was a little younger, a little more control. This one? Yeah. Galileo. There you go. That was lovely. That was nice. Yeah. You've heard of him? Yes? Yeah. Yeah.
I thought he was an artist.
Do we know her? We're familiar with Marie Curie? Yep. She is the only person, not woman, but the only person ever to win 2 Nobel Prizes in different fields. So she had a Nobel Prize in chemistry and a Nobel Prize in physics. She and her husband, prior to his death, discovered radiation and understood how alpha, beta, and gamma decay happens. And then she did a bunch of other stuff by herself after he passed away. This guy is Anders Celsius, Celsius scale, blah, blah, blah. Have you heard of Rosalind Franklin before? May have heard of her in biology class. Maybe not. I don't know. So have you heard of Watson and Crick before? Do you know who Watson and Crick are? Yep. They're the ones that discovered DNA, that figured out what DNA was. But really, who was it? It was Rosalind Franklin. She's a physicist, and she was the one that actually figured out what the shape of DNA is. But again, another one of those, they don't get shout outs anymore. So I feel like I need to do that. Niels Bohr. You guys have heard of the Bohr atom in chemistry, right? Yeah. Also a physicist. Just saying, Yeah. Anyway, there you go. So a little Valentine's love for you. Also, my other little PSA that I want to share with you, besides being Valentine's Day, it is also National Ferris Wheel Day. I don't know why it's National Ferris Wheel Day because it's February, and that seems like an unpleasant time to be on a Ferris wheel. And the PSA part of it is that it's National Organ Donor Day. So I'm putting this out there not because I'm trying to tell you what to do, because I know that lots of people have different beliefs and I don't want to impose my belief system on you. But I just want to let you know you have the opportunity when you go in to get your driver's license, right? That they ask you, do you want to be an organ donor? And you can say yes or no, and nobody bats an eye or judges. But if or when you perish, and let's be honest, in the grand scheme of things, all of us will at some point, right? I'm not trying to be dark or negative, but it's going to happen at some point, sometime. The organs from your body can save up to 8 lives. So your kidneys, your lungs, your heart, right? Like all of that stuff can be given to other people that are in need of it. So just putting it out there. It's like your final big gift to the world. So consider it and let your family know if you are an organ donor so that they know that you want that as well. All right. Friends, we're gonna refocus and get ourselves started. We're starting a new unit today. And we're gonna start talking about force again a little bit. So it's been a little while since we've really talked about forces. We were doing energy for a while and momentum and all that good stuff. So I just wanted to kind of get our brains back into this idea, okay? So I'm throwing a ranking task up here for you to look at. It says all the trailers and cars shown are identical. The trailers have different loads, so they have different masses, okay? In each case, the car and the boat trailer are moving at a constant speed shown, and then it asks you in each of those cases to rank the magnitude of the net force. Okay? Go ahead and pull your notes out because we are going to start with notes in just a minute, and this is the beginning of it. So go ahead and take a look. Take a look up here. Start to think. You are very welcome to start discussing right away. That's fine with me. I don't want this to take a super long time, but we're kind of getting our brains back into physics, back into forces. So we're going to go ahead and get started here. I hear lots of good physics conversation, but I don't want to, I want you to understand this, but this is part of a larger picture of what we're doing today and what we're doing this unit. So I don't want to belabor the point too much. So again, you've got trailers that have different loads. They have different masses, right? So different, where are we at here? Different loads. So we got different mass. And we've got different speeds, but it says that all the speeds are constant, right? Rank the magnitude of the net force. So if you have something on a board, hold it up so I can see it. If you don't, that's okay too, because I cut you off kind of fast. It's got BACD. Anything else? Didn't you guys have something on a board? Yeah. Then it got erased? All right. So let's talk it through, friends. It's been a while since we've dealt with forces, really, hasn't it? It has, and that's why I threw this out here so that you could, kind of grapple with it again. What does it mean to have a net force? Bigger picture, big philosophical conversation, question there. What does it mean, or what does it imply about an object if it has a net force acting?
Is it like its total force, like all of the power, energy?
Okay, so this is all of the forces added together, right? Is that kind of what you meant? Yeah, absolutely. So F-net literally means add up all the forces acting, right? And if we add up all the forces acting, then one of 3 things can happen. Are you with me there? So let's look at the frog sitting on the table. Tell me about the net force of the frog while he's sitting on the table. It's 0. Does that mean there are no forces acting on him? No. What forces are acting on the frog? Gravity, or the force of the earth acting on the frog. And which way does that one go?
No.
Okay, life is good. That's one force. And then there's also the table. Which way does the table pull or push? Up. How does the table's force up compare to the earth's force down?
Equal.
Equal. How do you know they're equal? The frog's not the frog. The frog is not flying. And Keely, what did you say? Okay, and it's not accelerating. Life is good so far? Okay. We're going to assume no air resistance because air resistance is annoying. If I let go of the frog, what's going to happen to him? He's going to fall, right? He's going to drop. He's going to move down. How many forces are acting on him? Again, assuming that there's no air resistance, so we're not trying to trick you. As he's falling. Now, 1. What is it? Gravity. Is F net 0 now? No, it's something other than 0. And how do you know that it's not 0?
It's accelerating.
It's accelerating. Okay? So let's use what we just said, what you just said out loud. I'm going to write that down. So F net is all the forces added together. That's what Madeline said, and I totally agree with that. So if F net is 0, then what do you know about there's something that we know? Acceleration is 0, right? Is that okay? If F net isn't 0, then what do we know about the acceleration? Not 0. This should not be a surprise. Is that correct? Are we okay here? Yeah, not a surprise. We've been saying this for a lot of months together. Okay? Does it go the other way as well? If the acceleration is not 0, does that mean that there's a non-zero net force? Does that make sense? If you see something accelerating, you know there's got to be a net force on it, right? If you see something not accelerating, what do you know about the net force acting on it? It's got to be 0. Okay. I'm going to give you 1 more minute with the problem. I want you to look at it, and I want you to answer the question. Go.
I said if you're moving at a speed, there's no acceleration. But now, this question.
I am not trying to trick you. There is no. Talk it through with your table mates, guys. You got this. Use your physics. A little bit. Bowling ball stories are wonderful. All right, what'd you say? What'd you say? Show me your page. Show me your boards. Hold on, Jacob. 0. Yes. There we go. Do you understand it? Fantastic. All right. So we're good? Everybody's happy. All right. So again, oops, you didn't see my little X. There it was. I had frozen. I apologize. If F net is 0, A is 0. If F net's not 0, A is not 0. Nothing that I've told you so far should be a surprise. Okay? Next part of the story. Here we go. All right. So I got this cute little cup. It is cute. It's got Diego on it and a turtle. And it's got some water in it now. So what I'd like you to do, I'm going to have you take a look up here. Again, I'm not trying to trick you. I want to make that very clear, right? We're just doing physics. So I've got 3 strings, but you can assume it's just 1 string because, you know, it's easier to draw 1 string, but not really easy to put a string through the middle and be able to hold it. That would be a little unstable. So anyway, there you go. I've got a string holding up a cup. I would like you to draw a free body diagram of this system.
All right.
Okay? Go ahead and draw it on your paper, then have a conversation and come up with an answer on your board, okay? So free body diagram of the cup and water, you can kind of put them together and call them a system and just call it the cup. Does that make sense? You don't have to like do them separately, like it's confusing.
There's water in the cup?
There is. I poured some out from my water bottle. Somebody saw me, I'm sure. Okay, there you go. They can vouch for me. Show me some free body diagrams, friends. Show me what you got. Force of the string on the cup, force of gravity's not a thing I can buy. Want to know what they are. We're just trying to be really good kids. But I can buy some, right? It's a thing. It's a thing. Do we agree that there are 2 forces? Yeah? Okay. So we agree that there are 2 forces. We agree. If this is my cup, that you've got which one? What do we have acting? Force of the earth, right? We're being really good kids.
So you don't want us to say gravity?
You could write FG if you really want to, if that makes you happy. Yeah. Okay, so you got the gravity on the cup, or the earth on the cup. What else? What else? Anything else? The string on the cup? Which way does that one go? Up. How do the force of the string and the force of the earth compare? Equal? How do you know? Blah, 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 blah. No acceleration? Blah, blah, blah. F net equals 0, blah, blah, blah. Right? All right, life is good. Okay. Kara, come here. And Jacob, come here.
Me.
Yeah, I think there's space. Right? Lay down.
Oh, yeah.
Lay down.
I lay down instead?
Both of you, lay down.
Oh.
Yep. So facing the ceiling, with your heads here, feet towards Zach. There you go. Right next to each other. There you go. Here. Oh yeah, I won't mess up. Why don't you scooch together just a little bit? I don't want to hit anybody. All right, you guys ready? Lily, do you want to lay down too?
Nope. No, I'm good. Sam can.
Are you sure? Okay. No, I'm not going to pour water on that. Now, I will say, I guess I said in the last class that I had never done this on Valentine's Day. I did last period though. So you ready? All right, ready? Do you trust me? It'll work.
No.
She's looking a little like I'm gonna make a mess. Okay. My head's you guys for that,
then maybe you shouldn't be so sure of yourself.
It's just part of the show, right? Okay. Here. The other side. Do you want to get up? Are you okay?
Yeah.
All right, here we go.
Oh my God.
Are you getting wet?
No.
Okay, good. All right. Did you want to do that again? Or are you
Was
okay?
there actually something in there?
Yeah. Do you want me to dump it on you?
What? No. What? That's
Do you want to do it again though, or
yeah.
no?
One more time.
Okay.
Because I was confused. I was paying attention.
What's that?
I
Wait, what did you say?
want
Not right now. So yes, there is water in here. Do you want to see the water? Or
I
do you-
can see.
Okay. All right. Here we go. All right. Here we go.
Yeah. The cup falls out.
There we go. You good?
Yeah.
Still happy?
Yeah.
Did you get wet, Jacob?
No.
Okay, cool. How about? All right. Woo! I'm good. I've never actually but funny story. You know how like Dixie cups, because they've got the wax on them, but if you like leave a Dixie cup too long, then the wax just deteriorates. So I used to have this other one, and I was like, "You getting wet? You getting wet?" And the kid's like, "Yeah." I'm like, "You are not." He's like, "Yeah," because it was like leaking out the bottom. Like the screw wasn't good anymore. It was kind of funny. I'm like, "Sorry, man." It was like just like a little bit. It was not, but it kind of a little bit defeated the purpose, but not the whole time. All right, so. Cara, did you get wet? Jacob, did you get wet? Okay, so no water then fell out of the cup. Can we all agree on that? Okay, so now my question for you, I'm not going to do it yet because I haven't dumped the water out, but I want you to draw a picture of the free body diagram of the cup when it was up here. So erase your board, have a conversation with your table mate, draw a free body diagram of the cup when it's at the top of the circle, okay? Go.
Yeah, that puts the water on the top. Because, like, it doesn't down.
I don't know that you're quite there yet, but I'm hearing some good conversation and I want to capitalize on it. So I've got this is my original. I'm going to go put my other one up on top here. So I've got my cup. Oops, I guess that's the bottom of the cup. There it is. So now Diego's upside down. And so what forces are you talking about acting on the cup? The force of the string. Do we all agree that the string is going to apply a force to the cup? Sure. Which way is it going to pull or push? Down. Good. That's awesome. So the string is pulling down. The force of the string on the cup, for sure. And the way we know that, for those of you that are not completely convinced of that, I've dumped the water out, by the way. I'm not going to make a mess here. There might be a little bit of drips in there. But anyway, the string can only pull in the direction that the string is, right? Last period, I had some people that wanted the string to push this way when it's up at the top, which does not make sense. Are you with me there? It does not make sense. So there's got to be something there. So the string is pulling down. Okay. Other forces acting on the cup. Okay, I'm hearing lots of things. Cara, did you say something? Oh. Did she actually?
No, these two people said force
Oh.
of gravity. Yeah, I said force of gravity.
Force of gravity. Okay. Which is the force of the earth. And which way is that one pulling or pushing? I was making assumptions without actually asking. Down, right? Yeah. Of course it pulls down. So the force of the earth on the cup. So that's Fg if you want it. And this is Ft if you want it. Okay. And are we good? No? Why not? What else is acting? The water. What do you mean the water? The water is pushing the cup up?
Like when it's upside down. Wouldn't the water be in?
So let's think about it. And we didn't talk about the water when it was down at the bottom, right? Because Madeline asked and I said, let's assume that the water and the cup are together. But weird stuff happens up here, right? So maybe instead of looking at the water and the cup here, or like instead of putting them together, let's maybe put them apart. So if you were going to take a look just at the water, now people want to do that because they want to show why the water's not falling. You with me there? So if you do that, then really we're talking about the cup. But is it the cup that Cara and Jacob were concerned about not falling? No. Was it the cup itself? What was it that you were concerned about falling?
The water.
The water itself. So let's look at, can we like make like a little like side note here to just look at some water? So if there's water, and I'm just talking about the water, what forces are acting on the water? The cup. Is that what you said?
Yeah, the cup.
Which way is the cup pulling or pushing on the water? It's pushing down, right? So we got the force of the cup on the water. That's an applied force, right? A contact force. What else is acting on the water? I heard somebody else over here say something. Gravity, the earth. On the water. What else is acting on the water? Yeah? I didn't touch the water.
No, but you touched the cup.
No, I didn't. I touched the string.
You touched the string, which is-
I touched the string, which touched the cup, which touched the water.
Yeah.
But remember that when we're talking about a force is an interaction between how many objects? Just two. Right? It's only two. It's the force of A on B or the force of B on A. And if there's a chain reaction, the force of A on B causes B on C causes C on D, but that doesn't mean that A hits D. Are you with me there? So the only way that you can have a force, and it's been a long time since we said this, which is why I love this conversation. The only way you can have a force is either a contact force, two things actually touching, or it could be gravity, the electromagnetic force, the strong force, or the weak force. We don't know anything about those, so let's not include those because that makes no sense to us. So it's got to be either touching, contact, or it's got to be gravity. Is there anything else touching the water besides the cup? The air, true. The air pushes on all directions. Right? So we have to draw that in all directions, so that would all kind of cancel out. You with me there? Yeah. Anything else?
Water.
Touching the water?
Yeah.
So we got internal forces, right? But internal forces, Newton's third law says that all those are going to cancel out. Anything else pulling or pushing on the water? It's okay to say no. No. Okay. The answer is no. The answer is no. This is the free body diagram of the water, you guys. It makes people mad though, doesn't it? Why are you upset, Courtney?
Because it's only like pushing it down, so why would it not fall?
Right. That's exactly right. That's why people get mad. Not like literally mad, but frustrated because the water should fall. Bakar, did the water fall and hit you?
Nope.
No? What about you, kid? No. So I have an opportunity for you, if you would like it. I could pour more water in here, and I could have you lay back down, and I could just take the water and go like this. What's going to happen to the water if I do that? Right? It's not going to stay there. You know that from enough life experience, right? So what's different about this versus what I did when they were laying there? What's that? I heard something like in this general direction. I'm spinning it, right? I'm spinning it. It's moving. Are you with me there? Right? If an object is moving, does it want to stop moving? No. If an object is moving, it wants to keep on moving. The only reason that it's going to change its motion is if it has a net force that's not zero. Are you with me there? Now, in the last class, when I was giving this example, I had to work really hard to find somebody who would have been ornery enough to do this. But in this class, I don't have to work very hard because Miss Lily, I could totally picture this happening, especially if Jacob was sitting down there, getting some sort of sharp scissors, such that as it's spinning around and spinning around and spinning around, she comes and the water right up here, she goes, boop. You could kind of picture her doing that, right? Like, I love you a lot, but I could, like, if any, like, maybe, right? Maybe? No, if I told you to, if I asked you to do that, would you do it? Okay, there you go. Yeah. Sure, Miss Kay, I'd do that for you. Yeah, so she cuts the string right up here. Where is the water going right now? It's going this way. Are you with me there? And the water wants to go this way. Why doesn't the water just keep going that way? Because the string is pulling the cup down. Are you with me there? The cup is pushing the water down. You with me? Is that okay? Okay. So as this thing spins around, let's go ahead and draw that circle in here. So it's going around in a circle. It's going like this, and it's going like this. It's going around in a circle. At the very top, when it's going in its circle, the cup and the water system, I'm going to call it all one thing because it makes it easier that way, is moving straight to the side. The water wants to go like this. Because a bowling ball rolling down a hallway, would it stop if there was no friction and no air resistance? No. It's got no reason to stop. It's just going to keep on going, right? F net equals 0. We're just going to keep on trucking. Same thing with water. If it's moving in this direction, the only reason that it's going to change direction and the only reason that it's going to accelerate is because there's a net force acting. Okay? This is the same thing that we said before. So here's the thing that we need to know. So this, I'm going to just label a couple things. And if you have not yet drawn this picture in your notes, I want you to do that now. Okay? Because we're going to start using this picture. And I want to make sure that you've got it written down so that you know what to do with it as well. Okay? So this is the velocity of the cup at the top of the circle. Okay? The velocity is going in this direction. My friends that recall their geometry, or maybe you're in calculus, depending on where you're at in your mathematical career, might recognize this line here relative to the circle. It starts with a T. What is this line relative to the circle? Anybody? It's tangent. Yes. The velocity of the cup relative to the circle is called the tangential. Come on, thing. Okay. Tangential meaning that it is perpendicular to the radius of the circle. So it wants to go that way, but these forces here are pulling it in. They're changing its direction. They're accelerating it. There's potential velocity, but the cup experiences a net force. Should have written that as F net, sorry. A net force toward the center. And remember, we said earlier that if there's a net force, that means there's got to be an acceleration. So a net force towards the center, which means an acceleration toward the center. Okay. And that net force towards the center has a very special name. The name comes from the word or the term center seeking. And the word is CENTRIPETAL. The word is centripetal. Okay? The word is centripetal. Centripetal means center seeking. Whenever you have something moving in a circle, it experiences this center seeking acceleration. Okay? I'm going to stop new content right there. I want to tell you two quick things. Is it okay if I click away, or are there people that are still writing? I don't want to rush you. Okay. I want to let you know that there are a couple of questions. These are conceptual questions that I want you to work on for tomorrow. Okay. So we've got a place to start, and we'll do the mathematics that goes with this a little bit more tomorrow. Okay. I also wanted to address the question of our the test that you just took, the corrections and all of that. So if you did not finish your corrections yesterday, and I know that it was a shorter day for us yesterday, please let me know when you can come in during any period, because I can just put you over there or send you into the study hall room, or before, after school, or Liberty time. You tell me when you can do it, and we'll make it work. Okay. I promised you some additional practice problems that I have not yet posted because my 7th period got a little nuts yesterday. So I will get those up, and as soon as I do, I will send you an email. Okay. If you took the test yesterday, I will get it graded tonight, and I will for sure get it back to you tomorrow. All right? Would you please, before you go, erase your boards? Take your boards and your markers and erasers back up and put them in the drawer. Okay? And then have a fantastic Valentine's Day, you guys.
Carla, you know Martina McBride?